This video is on how to create and understand graphs of certain trigonometric functions, namely the tangent, cotangent, cosecant, and secant functions. It corresponds to material found in section 6.5 of the textbook. Let's start by creating a graph of the tangent function. Just like we did for the sine and cosine functions, we are expressing tangent as a function of x so that we can graph it in the xy plane. We already know that the period of the tangent function is pi. And because the tangent of x is undefined for x equals pi over 2 and minus pi over 2, we want to avoid evaluating it at those points. So we choose the interval between minus pi over 2 and pi over 2, not including the endpoints, to get values of the tangent of x. The table on the left includes values of x for which we can readily obtain the tangent. The last column lists them in ordered pairs, which we can graph. And here's the resulting graph. Notice that the values of x are between minus pi over 3 and pi over 3. This is a good start, but the interval we're considering extends from minus pi over 2 to pi over 2, so we need to find a way to graph the rest of the function in the interval. Based on our prior study of the tangent function, we know that it is undefined at certain values of x, such as minus pi over 2, 3 pi over 2, and so on, all expressed in radians. This means that there are vertical asymptotes at all these values of x. So how does tangent of x behave as it approaches pi over 2? We use the trigonometric identity tangent of x equals sine of x over cosine of x to help us find out. As x gets larger and approaches pi over 2, the sine of x approaches 1. And as x gets larger and approaches pi over 2, the cosine of x approaches 0. So what we have is a fraction whose numerator is getting closer to 1 and whose denominator is getting smaller and smaller and closer to 0. This means that the fraction is getting larger and larger and is in fact approaching infinity. Now at the other end of the interval we're considering, that is, as we're getting closer and closer to minus pi over 2, x is getting smaller. And as it approaches minus pi over 2, this means that sine of x is approaching negative 1, and cosine of x is approaching 0. Since tangent of x is the ratio of these functions, as x approaches minus pi over 2, the numerator is almost minus 1, and the denominator is getting smaller and smaller, closer and closer to 0, so the fraction approaches minus infinity. We use all this information, along with the points plotted in the previous graph, to graph a complete cycle of the tangent of x. And since tangent of x is periodic, this means we can graph the entire function. Tangent of x is an odd function. It's symmetric about the origin, and its domain includes all values of x except those at odd multiples of pi over 2. Just as we've done for other functions, we can use transformations to graph functions based on tangent of x. Let's begin with the basic function y equals tangent of x. We know how to graph this, and the graph is shown here on the left side of the slide. When we multiply tangent of x by 2, the graph is vertically stretched by a factor of 2. The asymptotes remain the same as they were before. We can then subtract 1 from 2 tangent of x, and this shifts the entire graph down by 1 unit. Now let's look at another transformation. Again, we start with the basic tangent function. Next, we multiply it by 3, resulting in 3 times tangent of x. The graph is vertically stretched by a factor of 3. Next, we perform a horizontal compression, where we replace x, the argument of the tangent function, with 2x. This causes the graph to be compressed so that the asymptotes are now at odd multiples of pi over 4. As we might have expected, the cotangent function shares many of the characteristics of the tangent function, as it is its reciprocal, defined as the ratio of cosine x to sine x. This means that cotangent of x is undefined for x equals minus pi, 0, pi, and so on, which are values of x for which sine of x is equal to 0. There are vertical asymptotes for x equal to the integer multiples of pi. Knowing this, we choose the interval 0 pi, 0 comma pi, to find values of cotangent of x, and we evaluate the function at selected values of x within this interval, the ones for which we can easily find the cotangent. The values of x we've chosen, along with their cotangents, are listed in the table on the left. We can plot these ordered pairs and, using the same kind of analysis we did for the tangent function, that is, taking the limit of the numerator and the denominator functions separately as we approach an asymptote, we can plot the cotangent function over the interval 0 to pi. And since cotangent of x is periodic with period pi, we can plot the entire thing. The first step in graphing the cosecant function is recalling that cosecant of x is the reciprocal of sine of x. Since the denominator of cosecant of x cannot equal 0, we have to exclude values of x for which sine of x is equal to 0, which are the integer multiples of pi. These values of x are the locations of vertical asymptotes of cosecant of x. And here is a plot of cosecant of x. It's plotted here on this graph in blue. The graph of sine of x is plotted in black, and it's good that they're plotted together because the functions are so closely related, and the relationship between the functions is manifested in the graph. We see that the period of cosecant of x is 2 pi. Also, where sine of x is equal to 0, the cosecant of x goes to infinity, where sine of x is positive, or minus infinity, where sine of x is negative. Finally, we see that there are 2 times within each period of cosecant of x that it is equal to sine of x. The secant function is in many ways like the cosecant function. They're both reciprocal functions. Here, secant of x is the reciprocal of cosine of x. Because that's true, and because the denominator of the secant of x cannot equal 0, this means the secant of x is undefined when cosine of x is equal to 0, and cosine of x equals 0 when x is an odd multiple of pi over 2. As we expected, these values of x are the locations of vertical asymptotes of the secant of x. Now here's a graph of secant of x, and it's graphed in blue, and it's graphed along with cosine of x, and it's shown in black. This graph is very similar to the graph that we looked at previously, the one that showed cosecant of x and sine of x plotted together. Here we see that secant of x has a period of 2 pi, and that it goes to infinity when cosine of x is positive and approaching 0, and it goes to minus infinity when cosine of x is negative and approaching 0. We also see that for 2 values of x in each period, the secant of x is equal to the cosine of x. The graphs of cosecant of x and secant of x are not as easy to work with as those of the other trig functions, but we can perform transformations on them just as we did for graphs of other functions. We just have to be a bit more careful to get them right. So let's perform a transformation of the cosecant of x to obtain a graph for a different, similar function. First, we multiply the function by 2, which corresponds to a vertical stretch of the graph by a factor of 2. Next, we subtract 1 from the function, and this means we shift the entire graph vertically downward by 1 unit.